Hello all, this is the video answer key to the Unit G review guide in preparation for the test on stoichiometry. In 2025, the test will be on Wednesday, March 19th. The format will look like this, and remember, you can get extra credit points if you do this review guide. I'm literally giving you the answers. If you do it and you want to check your answers, you can use this answer key to help you prepare. So I'm not going to write the actual definitions for these. These are things you can look up on your own. If you have trouble with any of these terms, you should seek help. You can seek help from a classmate, a tutor, or you come see me after school or during a free period. The first question deals with, this is my favorite reaction in chemistry. It's called the Haber-Bosch equation, and it has a lot of historical significance and human rights significance. Also, I like that it has an interesting ratio of coefficients. None of them are the same. So the first question says to balance the chemical reaction, and using the coefficients, you can balance it to have a 1 to 3 to 2 ratio. And when it tells you to convert from grams of one chemical to grams of another chemical, this is the big idea from this whole unit. You have to go to these middle steps of moles. And so if you change grams of one chemical into moles of that chemical, we use the molar mass from the periodic table. To go from moles of one chemical to moles of another, you have to use the molar ratio from the chemical equation. So for this example, 1 mole of nitrogen will produce 2 moles of ammonia. And then lastly, if you're trying to go from moles to grams again, you need to use the molar mass from the periodic table. So each of these questions, they all deal with converting amounts of nitrogen into amounts of ammonia, but they ask from different starting points. So this question goes from moles of nitrogen to moles of ammonia. That's what it's asking you to do. So you're really just doing the middle step. So you really only have moles to moles. So that's this one. In question part D, it gives you moles of nitrogen, but asks for grams of ammonia. So in part D, you got like a two-stepper. You got to go from moles to moles and then moles to grams. So this is really the work for step D. And then in part E, it goes all the way from grams of nitrogen to grams of ammonia. So part D is all of these. You do all the steps. It's the old three-stepper. It's like a waltz. You have to go from grams of one into grams of the product. So we'll start with the moles to moles. If you are going from moles of nitrogen to moles of ammonia, that's only the one-step conversion. So we're going from nitrogen to ammonia, which is a 1 to 2 ratio. So if you have 1 mole of nitrogen, you would produce 2 moles of ammonia. But if you have 6 moles, of these, you would produce 12 of these. So when you set up your dimensional analysis, it should be that the 2 is over top of the 1. If you set it up this way, you can see, I'll try to use the right colors, moles of ammonia are present in the numerator and the denominator, so they should cancel. And then you're left with moles of ammonia as the product. In part D, this is the two-stepper. You got to go from moles of nitrogen to moles of ammonia, and then moles of ammonia to grams of ammonia. So each of these has their own little equalities. If you write the number of moles as equivalents, you get a 1 to 2 ratio of nitrogen to ammonia. And then going from moles of ammonia to grams of ammonia, you need the molar mass from the periodic table. So 1 mole of ammonia is 17 grams. So if you have 12 moles, that's actually kind of a lot. We will never deal with this much, this amount of a gas in class, 12 moles of ammonia. It would take up like over 200 liters of space. But regardless, so 12 moles of nitrogen would produce 24 moles of ammonia. If you're going moles to moles, you can just look at the reaction. So 12 gets doubled, and then you have to change it from moles to grams. So if you follow the units, moles of nitrogen cancel, and then moles of ammonia cancel, and so you should be left with grams of ammonia if you do the math all the way across. 12 times 2 times 17.04 gives you 408.96. And if you round it to two significant figures, it should end up 410 grams of ammonia. The last question asks you to go all the way from grams of one to grams of the other. So you have the two middle steps. Grams of nitrogen to moles of nitrogen. You use the molar mass from the periodic table, so grams cancel. Moles of nitrogen to moles of ammonia, so you have to double it, and you can see that the units cancel. And then once you get to moles of ammonia, you use the molar mass from the periodic table, so those units all cancel. If you do the math and you round it to the three significant figures, because you had three significant figures to start with, so 1, 2, 3, round it based on the number that comes after, you end up with a final answer of 11.1 grams of ammonia. So this one problem right here shows all of the steps. You're either going from moles of one to moles of another, or you're going from moles of one to grams of a product, or the largest, most calculations that you would have for a problem is grams of one to grams of another. Question 3 is a good one because it asks you to think about applying the ideas of stoichiometry. And if you ever caught on fire, you're supposed to stop, drop, and roll. Really, what you're trying to do is you're trying to make oxygen the limiting reactant. You don't want oxygen. If you're on fire, you want to stop that chemical reaction. One way to stop that chemical reaction is to limit the exposure of the reaction to the oxygen that's in you, in the air around you. All right, so there's a lot of oxygen in the air. And if something is burning, it requires oxygen. So consider any, I'll use a different color. Consider any reaction that burns. You're gonna make carbon dioxide and water. All right, so if your clothes are made of cotton, there's lots of carbohydrates in cotton. So cotton can react with oxygen to burn. It gives off heat and light, but it also produces these two things. If you can limit the oxygen, then you'll have a lot of cotton left over. So your cotton or your fabric would be the excess reactant. And we're trying to limit the amount of oxygen that is exposed to it by rolling or putting a blanket on it or something. So if you can find a way to limit the amount of oxygen that is reaching the cotton, then you'll be able to put the fire out. The next question asks you, if you make this much, how much water would you make? Now, it asks for it in grams, and this is a little bit different than most of the equations. Usually we take a reactant and produce a product. But the good thing about chemical reactions is that these ratios are true no matter whether they are reactants or products or both reactants. So if you are performing in a chemical reaction and you're producing an amount of product, you would produce a proportionally equal amount of the other product. So if however much you have makes 1.73 grams, you can change grams of this chemical into grams of this chemical. You still have to follow the pathway though. Grams of one chemical to moles, and then the molar ratio, that's the thing that will be equal. So if you made 4 moles of water, you would have also made 2 moles of sodium sulfate. We don't make 2 moles though, we make this much, and we make it in grams, so you gotta change the grams to moles, then you can go moles to moles, then you can go moles to grams. So here are the equalities necessary for this problem. And then when you set up the multiplications so that the units cancel, you start with 1.73 grams of sodium sulfate, so those cancel. Then you have sodium sulfate in moles, so those should cancel. Then you get it to moles of water, so those should cancel. When you do the math, 0.4389 rounds to 3 significant figures by changing to 0.439 grams of water. Question 5 tells you that you have hydrogen peroxide and it decomposes to water and oxygen. In order to do stoichiometry, you need an equation. So here's the balanced chemical equation. I started by writing just the hydrogen peroxide decomposing to make water and oxygen. And then I balanced it. So the formulas were given for hydrogen peroxide, but not water. Hopefully you know what waters is. And bro, you've got to remember oxygen is O2. So when hydrogen peroxide decomposes to make water and oxygen, then you need 2 moles of hydrogen peroxide to produce 2 moles of water. And I know there's no number here, but really that means there's 1 mole of oxygen. So you can add this 1 in that space. Or don't, just understand there's a 1 there. So the question tells you grams of hydrogen peroxide and asks for grams of oxygen. So you got to go the old 3-stepper. So you got 1, 2, 3 steps of conversion. And these are the equalities. Now, this is the number from the problem, so that's what you should start with. Then you use the conversion factors to show that the units cancel. So grams of water cancels there. Oh, not water, that's hydrogen peroxide. Grams of hydrogen peroxide cancels here. Now going from moles of hydrogen peroxide to moles of oxygen, you can show the units there cancel. And then moles of oxygen to grams of oxygen cancels there. When you round it to 3 significant figures, you should end with 6.44 grams of oxygen. The last, question 6 tells you that you take magnesium and you react it with hydrochloric acid. And it produces hydrogen, which is another one of the diatomics, and magnesium chloride. So this is a single replacement reaction. So first you need to write the reaction. It doesn't actually tell you to do that, but you can't do stoichiometry without a chemical equation. So if you take magnesium and react it with hydrochloric acid, you make hydrogen and magnesium chloride. Now there's no numbers in front of these, but after it's balanced, technically those numbers are 1s. So if you do or don't, just understand there's a 1 here. That means for every 1 mole of magnesium, you need 2 moles of hydrochloric acid. In this example, it just asks you to change moles of magnesium into moles of hydrogen. So this is a 1-stepper. You have moles of magnesium, 2 moles of hydrogen, and the molar ratio is 1 to 1. So this is about as simple as the problems get. You just have to understand, if you're going moles to moles, then you just use only the middle part of that magic pathway. So moles to moles, 3.75 moles of magnesium. You can see those units do cancel, so you should end with moles of hydrogen. Question 7 is the first example on this review guide that deals with the concept of limiting reactant. Now, the way this question is written says that you have 2 different compounds that contain nitrogen. We have nitrogen tetroxide and hydrazine. So here are the formulas. So those 2 compounds react to produce nitrogen and water. So here's the reaction. You just have to understand that this reacts with this to produce nitrogen and water. And then you have to balance it. So when I wrote it, I just wrote the formulas, and then I balanced because there are, I started with a hydrogen because nitrogen is all by itself. So there's 4 hydrogens here. I don't remember how I did this. Oh, I started with the oxygens. There's 4 oxygens, so I put a 4 there, which made there be 8 hydrogens. So then you could double this one to get to 8 hydrogens. Now you can get to the nitrogens all by itself. So because you have 2 here and 2 sets of 2 here, so that's 4 plus 2 is 6. You have 6 total nitrogens. You have to have 3 molecules of nitrogens to get 6 nitrogen atoms. So this is the equation. Here's how you balance it. The phase symbols are these little G's underneath. Okay, it doesn't tell you what phase of water, but it's going to be a guess. Now, part B tells you you have 2 different amounts. In so many of the questions up to this point, the problem has always said something like in an excess amount or with an unlimited amount of one of the reactants. In this case, the reactants are not unlimited. That means one of them is going to limit the amount of product. If the reactants are not unlimited, you got to do both stoichiometry problems. Okay, so if it gives you grams of one reactant, you got to figure out how much product could you make with that starting amount. Okay, and so I identify, like, here are the two different reactants. So this one goes right here, and then separately this one is a separate calculation. So these are two different calculations, and you have to use each of them to figure out which one is going to limit the amount of product that you can make. So in this example, you started with 8 grams of nitrogen tetroxide. So we go grams to moles, moles to moles, moles to grams. If you need help with these middle steps, you can come see me, but I'm just not showing step A or B of the pathways anymore or the conversion factors. I'm just doing it. So this is the molar mass. This is from the molar ratio. There's 3 moles of nitrogen for every 1 mole of nitrogen tetroxide. And then here's the molar mass for nitrogen again. So if you do the math all the way across, you end up with this number from the calculator, round it to 3 sig figs to produce 7.31 grams of nitrogen. So I'm going to summarize this whole calculation right here with this statement. If you have 8 grams of nitrogen tetroxide, you can make 7.31 grams of a nitrogen. That's if the other one is unlimited. If you do the same thinking and calculations for the other chemical, if you start with 4 grams of hydrazine with an unlimited amount of nitrogen tetroxide, if you start with 4 grams of this, you can only make 5.25 grams of nitrogen. So thinking about like our bike example from very early in the unit, the reactant which limits the amount of product, that's the one that's limiting. So this chemical right here is the one that limits the total amount of product you could make. Because if you have 4 grams, you can only make 5 grams-ish of nitrogen. If you have 8 grams of this, you could make up to 7 grams if you had more of this stuff. But you don't. You're limited by the amount of hydrazine, which means you're going to have some of this stuff is left over. Okay, so the excess reactant is the nitrogen tetroxide. So I have one more example of how you can determine limiting reactant in question 8. So my version of question 8 did not have this step, but you do need to write the balanced chemical equation if you're going to make any sort of predictions using stoichiometry. So it says that iron reacts with water to make iron oxide and hydrogen gas. This chemical is a mixture of iron 2 and iron 3. It has its own name. It's called magnetite. Let's just accept that the formula we make is Fe3O4. So if you understand that iron reacts with water to make Fe3O4 and hydrogen, then when you balance it, you need 3 irons, 4 waters, 1 magnetite, and 4 hydrogens. So this is similar to the question before. You have amounts of both reactants. They are not unlimited. If it is not an unlimited amount, you have to do both of them. If you do the stoichiometry calculations for both reactants, the one that produces less product is the limiting. So to walk through each calculation, if you take grams of iron to moles of iron to moles of magnetite, and then moles of magnetite to grams of magnetite, you see that you can only make 23.2 grams of product if you start with 16.8 grams of iron. But if you go from grams of water into grams of product, you go grams of water to moles of water to moles of magnetite, and then moles of magnetite to grams of magnetite. If you started with 10 grams of water, you could make 32 grams of magnetite. But that's if you have an unlimited amount of iron. We don't have an unlimited amount of iron. We only have about 17 grams of iron. So with these two amounts of reactants, the amount of product that you could make, the maximum amount of product you could make, is this one, which is less than that one, because we're limited by the amount of iron. So So the question is, which one is limiting? It's iron, because it makes less than it makes if you had water. And here, let's demonstrate. If you have that amount of iron, how much water would you need? So we can go from an amount of iron measured in grams to an amount of water required measured in grams, but you still have to do the grams to moles, moles to moles, moles to grams. So 16.8 grams of iron to moles of iron to moles of water to grams of water means if you had 16.8 grams of iron, you only need 7.23 grams of water. You got 10 grams of water, so you have more water than you need. That means that water is going to be the excess reactant. Sometimes we call them reagents. Sometimes, so in this example, you only need 7.23 grams to react with 16.8 grams of iron. That means you have some left over. Now, if you did this experiment and you actually produced 21.7 grams, when you determine percent yield, just like in the problem before, you take the experimental or the actual amount produced and divide it by the theoretical amount, and then you want to make it a percent, so we multiply by 100. So in this example, you would have had a percent yield of 93.53%. This is the end of the review guide. If you have questions before your test, it would be a good idea to go see your teacher or JHS tutor or talk to a friend who knows what they're doing. But good luck prepping for your test. I hope you do really well.